Let's just jump right into this. Welcome to The Explainer. Today, we are looking at something absolutely mind-blowing. We are going to dive deep into one of the most astonishing pieces of engineering in human history. Okay, let's dive into this. We're zooming straight into the microscopic, insanely complex world of graphics processing units, or GPUs.
Now, to make sure we don't get completely lost in all this silicon, here's our roadmap for today. Number 1, the scale of GPU power. 2, CPUs versus GPUs. 3, inside the GPU architecture. 4, feeding the beast with GDDR6X. 5, parallel processing using SIMD and SIMT. And finally, 6, looking beyond gaming to AI and crypto. All right, let's kick things off with section 1, the scale of GPU power.
So, before we can even begin to understand how a GPU works, we really need to wrap our heads around the sheer volume of math required here. Let me ask you this. How many calculations per second do you think are needed to run modern video games with incredibly realistic graphics? To give you some context, back in 1996, running a game like Mario 64 took about 100 million calculations a second. Skip to 2011, Minecraft required 100 billion. But to run a massive, ultra-realistic modern title like Cyberpunk 2077,
You literally need a machine capable of performing 36 trillion calculations every single second. 36 trillion. It is just a completely unimaginably large number.
Let's try to actually visualize that, because it's so massive. Imagine doing a long multiplication problem, just one, every second. To equal the output of a modern graphics card doing 36 trillion calculations a second, we would need 4,400 Earths filled with people, and every single person on those planets would have to be doing one calculation every single second, together. That is the unimaginable volume of data processing happening inside that little box sitting right there on your desk.
Moving right along to section 2, CPUs versus GPUs.
Now you might be wondering, how does this staggering power compare to a traditional CPU? Well, it really boils down to this classic analogy, the jumbo jet versus the cargo ship. Think of a modern CPU as a jumbo jet. It might have around 24 cores. It is highly flexible. It can fly to tens of thousands of different airports, and it executes a few incredibly complex calculations extremely fast. It's totally perfect for running your operating system or interfacing with networks. But the GPU? The GPU is a massive cargo ship. It could have over 10,000 cores, but it's totally inflexible. It only travels between very specific ports, and there is no way it could run an operating system. The individual calculations might be executed a bit slower, but its cargo capacity for bulk, simple math, it's absolutely colossal.
Which brings us to section 3, inside the GPU architecture.
Okay, we are now popping the hood and zooming directly into the physical chip itself. And the microscopic organization here is just beautiful. We're looking at the GA102 chip, built from 28.3 billion transistors. It is perfectly hierarchical. The chip is divided into 7 graphics processing clusters. Zoom in a bit, and each of those clusters has 12 streaming multiprocessors. Zoom in again, each multiprocessor has 4 warps and 1 ray tracing core. Zoom in one final time, and inside each warp you will find 32 CUDA cores and 1 tensor core. It's literally this breathtaking, fractal-like structure of pure computational power.
And notice how this division of labor builds out across the entire GPU. You've got these 3 different types of cores doing the heavy lifting. The 10,752 CUDA cores are your basic, simple binary calculators, perfect for running video games. Then you have the 336 tensor cores, which handle complex matrix math for AI and geometric transformations. And finally, those 84 ray tracing cores, they are dedicated exclusively to executing complex ray tracing algorithms to give you that insanely realistic lighting.
But here is a truly fascinating industry secret for you. It's called binning. Did you know that a 3080, a 3080 Ti, a 3090, and a 3090 Ti graphics card all use the exact same GA102 chip design? Seriously, they do. During the manufacturing process, tiny little defects, like a microscopic particle of dust, can ruin a sector of the chip. But instead of throwing that whole, incredibly expensive chip away, engineers just permanently deactivate the damaged streaming multiprocessors. So a completely flawless chip, that becomes your top-tier 3090 Ti. But a chip that has 16 deactivated multiprocessors because of manufacturing defects, they just box that up, categorize it, and sell it as a lower-tier 3080. It's brilliant.
Let's zoom all the way down to just one single CUDA core. This tiny little unit alone contains roughly 410,000 transistors.
And its primary job? Something called fused multiply and add. Basically, it just calculates a times b plus c using 32-bit floating point numbers. It's essentially scientific notation. It completes one multiply and one add operation every single clock cycle. So when you multiply that by over 10,000 cores all running at 1.7 gigahertz, well, that's exactly how you get our 36 trillion calculations a second.
All right, Section 4, feeding the beast with GDDR6X. So to actually perform 36 trillion calculations, these cores have to be fed mountains of data constantly. The GPU itself only has a tiny 6 megabyte level 2 cache for onboard storage. I mean, that is basically nothing. So it relies incredibly heavily on its external graphics memory. Think about this bandwidth comparison. A standard CPU DRAM might transfer data at around 64 gigabytes a second. That's fast, right? But the GPU's GDDR6X memory, it transfers a staggering 1.15 terabytes a second. Going back to our analogy, it's like having dozens of massive cranes loading up our cargo ship all at the exact same time, ensuring those cores never ever run out of numbers to crunch.
And how do they actually achieve that insane bandwidth? Well, cutting-edge memory from Micron actually moves completely beyond standard ones and zeros. Using an encoding scheme called PAM3, they utilize 3 different voltage levels, 0, 1, and -1. By encoding 3 binary bits into 2 of these ternary digits, they can transmit 276 binary bits of data using only 176 signals over the wire. They are physically squeezing more data through the exact same physical space. It's just genius engineering.
Now for Section 5, parallel processing with SIMD and SIMT.
Let's shift gears from the physical hardware over to the computational logic. Video game rendering and crypto mining actually fall into a very real, highly technical computer science category known as embarrassingly parallel. I always love that name. It just means these are problems where little to no effort is needed to divide the work up into separate, completely independent parallel tasks that don't rely on each other at all.
To see this in action, imagine rendering a 3D cowboy hat. This perfectly illustrates how GPUs handle these embarrassingly parallel problems using SIMD, which stands for Single Instruction, Multiple Data. Let's say our hat is made up of 14,000 vertices in model space around an origin point. To place that hat into the game world, you literally write one single instruction. Add the origin's position in world space to one model vertex. Then, because none of those vertices depend on each other, you just copy and apply that exact same instruction to the other 14,000 vertices simultaneously across all your thousands of cores. One instruction applied to multiple data points.
But, as you'd expect, GPUs have evolved over time. In traditional SIMD, the 33 threads in a warp had to execute their instructions in exact lockstep, kind of like an army marching in perfect formation. But if one thread hit a branch in the code and needed to do something different, things got really messy. So modern post-2016 GPUs moved to SIMT, Single Instruction, Multiple Threads. Now, the threads still receive the same instruction, but they possess unique program counters, which allows them to progress at completely different rates. This gives developers crucial flexibility for handling complex code branching.
Oh, and here's a really fine historical fact for you. The term warp that we've been using to describe a bundle of 32 threads, you might think it comes from Star Trek warp drives, right? No way. It actually derives from weaving. Specifically, the Jacquard loom from way back in 1804. That loom used early programmable punch cards to select specific threads for intricate patterns. So cool how modern tech terminology is woven right into history, right?
And finally, Section 6, Beyond Gaming, into AI and Crypto.
Because look, this massive computational power is definitely not just for rendering video games anymore. GPUs were literally the early engines of the Bitcoin boom. Basically, Bitcoin mining acts as a massive mathematical lottery, where GPUs run the SH256 hashing algorithm. By constantly tweaking a random number called a nonce, a single GPU could generate 95 million random lottery tickets every single second, hunting for that winning hash. Though, to be totally fair, today GPUs have largely been replaced by specialized ASICs that can perform an absurd 250 trillion hashes a second.
But where GPUs absolutely dominate today is artificial intelligence. Remember those tensor cores we talked about earlier? They are purpose-built for the exact type of math that AI neural networks demand. Instead of doing simple a times b plus c for single numbers, tensor cores execute massive concurrent matrix multiplication and addition operations. They are multiplying and adding entire matrices of data simultaneously. Generative AI requires trillions of these matrix calculations just to process human language or create a single image.
Which leaves us with a final, pretty mind-bending question.
We've seen how 28 billion microscopic transistors can work in perfect unison to perform trillions of calculations every single second. But with generative AI now demanding quadrillions of matrix calculations, pushing the absolute boundaries of what silicon can physically handle, what will the next astonishing leap in microscopic engineering actually look like? It's a question that makes you look at the computer you're using right now in a completely new light. Thanks so much for joining me on this explainer. I hope you found this deep dive into the hardware just as absolutely fascinating as I did.